Hi, this is Tim. Today's question is from Ryan, who asked, what size wire is required to carry out the Veritasium electrical experiment? Now, if you haven't caught that video, then here is the general gist of it.
Imagine you have a giant circuit consisting of a battery, a switch, a light bulb, and two wires which are each 300,000 kilometers long. That is the distance light travels in 1 second. So they would reach out halfway to the moon and then come back to be connected to the light bulb, which is 1 meter away. Now the question is, after I close this switch, how long would it take for the bulb to light up? Is it half a second, 1 second, 2 seconds, 1/c seconds, or none of the above? Now you have to make some simplifying assumptions about this circuit, like the wires have to have no resistance, otherwise this wouldn't work, and the light bulb has to turn on immediately when current passes through it.
He makes a big assumption there that wire has zero resistance. And he does that because he's trying to prove another point, but I see a lot of you do that also. So I want to use this as a learning opportunity to learn about voltage drop. Also, I don't believe he is correct, but there are a lot of people already hitting on that. So if you want to learn more, just search for Veritasium electrical misconception. You're going to get a lot of answers out there disputing this, and mainly you're going to get his, and you should watch it. It is interesting, and it does make you think about electricity. Through every length of wire, there is resistance. If there isn't resistance, then you do have a superconductor. Now, superconductors are something we definitely don't cover on this channel, and they don't always obey things that we traditionally think of as the way electricity works. So we're not going to go there. We're going to talk about copper wire. Throughout this length of wire, we are going to have resistance. And if we have current and we have resistance, then we are going to be consuming power in this wire. And you will not get full voltage at the other end. So first, how do we calculate voltage drop? Voltage drop is going to be I times L times R divided by 1,000. Where I is going to be our amps, L is going to be our length, and R is going to be our resistance per 1,000 foot. And you'll find this rating for every size wire. Now, Ryan, we're going to have to make some assumptions ourselves to make this happen, because in this equation, we know our length. He's made an assumption on this, but we don't know the amps of it. And so I'm just going to throw out that it's 1 amp. And I'm doing that just because we got to throw something at it. So I'm going to say that we're running 1 amp. And just for our initial reality, just so we can see how this should work before we try to go halfway to the moon in the back, our length is going to be 30 feet instead of 300,000 kilometers. And then our resistance, we're going to use 14 gauge wire. And the resistance is going to be 2.525 per 1,000 foot for 14 AWG. So now if we go back to this equation, we can plug in these numbers. So voltage drop is going to be 1, which is our number of amps, times 60. Because remember, we're going 30 feet out, we got to go 30 feet back. Then we have our resistance per 1,000 feet, which is 2.525. And then we're going to divide that by 1,000 to get our units the same. So that is going to come up to 0.1515 volts. Now notice in this voltage drop equation, we didn't actually have to give it our incoming power. I didn't tell it whether it's 120 or 12 or anything. Voltage drop is going to be based off of current times resistance. So notice this right here is amps or current, and this right here is our resistance, and this is our foot, which is used to calculate this resistance. So amps times resistance is going to be voltage. It doesn't care yet whether we're at 12 volt or 120. Now he had a battery, and I believe in the end he did say it was a 12 volt battery. So what we're going to do now is we're going to calculate the percent of voltage drop. So to calculate the percent of voltage drop, we're going to take that voltage drop and divide it by whatever our voltage was times 100. 0.1515, which was our voltage drop, divided by 12 is going to be 1.26%. Now the next crazy question we got to know is, what is our acceptable voltage drop? Well, for the most part, when you're sizing wire, 3% is acceptable. Some people say 5. I'm just going to throw 3 out there. So now we can back figure that voltage drop percent and figure out what our maximum voltage drop is. So our maximum voltage drop is 3%. So voltage drop in percent equaled voltage drop divided by volts. Well, we can do a little math here and spin this around, and now we're going to have voltage drop equals volts times that volt percent. Or 12 times 0.03, our maximum voltage drop for 3% is 0.36 volts. So if you were to measure, let's say 11.5 volts, which is greater than 0.36 volts on the other end of the line, then you have exceeded that 3% voltage drop. Now let's answer your final question, Ryan. And this one is going to get a little crazy because you did ask me to wire a switch halfway to the moon and back. But we can take that voltage drop and we can reconfigure that equation for the resistance. And so in this case, we had voltage drop equals amps times length times resistance per 1,000 feet divided by 1,000. Well, doing a little math here, we can figure out that R, or our resistance per 1,000 feet, equals voltage drop times 1,000 divided by amps divided by length. Now my length is in feet because usually I'm running a circuit maybe 100 feet. I don't ever do it in kilometers or anything like that. But again, it was 300,000 kilometers. Our wire has to go out and our wire has to come back. And that's going to be 984,251,969 feet. And so plugging that in, resistance equals voltage drop times 1,000 divided by amps divided by length. And we plug our numbers in. That means our resistance per 1,000 feet equals 0.36, which was our maximum voltage drop. That's going to give us 3%. Times 1,000 divided by 1 divided by 984,251,969. And that means our maximum resistance is 0.000003658. I may be off by a decimal there, but all right, we're already at the moon, so let's go ahead and finish this up. Now, when I go to Lowe's, the maximum size wire I can usually find is usually a 4/0 or something. And so the resistance per 1,000 foot of 4/0 cable is going to be 0.049 ohms. Should have had an ohm signal there. And if you were to put 133,967 4/0 wires together in parallel, you should be able to get a signal halfway to the moon and back with a 3% voltage drop. Now, I have a question. Is there even that much copper on Earth? Does anybody want to address that one? Check out the original video here. Till next time.